So shortest problem is asking us shortest path from a vertex S, from a given vertex S, to a destination vertex T. It is a directed path. Find the directed path from S to T with the property that such that there is no other path that has a lower weight, such that there is no other path with lower weight. Okay, so this is our problem. So let's say we are given a graph G that consists of vertices and edges, and it has some weights. They are declared from in edges and in real numbers. So we should find a path P which goes from V1 to V2 to V3, goes up to Vk, and of course this path has a weight, let's say this path has a weight Vp that's equal to sum of the edges from 1 to k minus 1. I need the weight of Vi plus 1. If you add them up, so you will get the cost of your path. So let's say if you have V1 to V2 and there is another path to V3 and it has to V4, and this is of length 2, 5 and 4, so the total weight of this short path is 2 plus 5 plus 4, which is equal to 11, shortest path. Okay, so shortest path from V1 to V4 is equal to 11. Okay, so this is our problem and we need to come up with a solution to solve this problem. Actually, before asking even how can we solve the problem, a solution idea comes to my mind and I would like to discuss if it's a good idea or not. So solution idea, find all the paths from U to V. So I will say the solution idea. I have a perfect idea. So find all the paths from U to V, or from S to V, as we say, source to destination V, then choose the minimum one, minimum cost. Huge runtime. Why huge runtime? So that makes me ask the following question. Question: what is the rate of number of paths to vertices? What is the rate of number of paths to vertices? Exponential? Is it exponential or polynomial or linear? Can it be linear or polynomial? Number of paths. Is it linear? I mean, so it's a multiple of V, or it's polynomial number of paths, V square or V to the something, or maybe it's exponential. Anybody has idea? Number of paths from S to V. So let's say I have and starting S and I have a V here, is really number of paths from S to V exponential? Or is it polynomial maybe? Kaushik insists on, since you could choose either vertex to be included or not included in the path, actually it is exponential. So for example, you see here, how many different paths do I have from S to V? Can I get an answer from anybody else? How many different paths do I have from S to V in this graph that I have drawn? How many different paths are there from S to V? Here. 1, 2, 3, and 4. Yes, there are 4 different paths. Either I come like, let's do it with a different pen. Either I come like this, or 1, 2, or 1, 3. So this one, 4. Okay, so I have 4 different paths. If I add 2 more vertices here, if I would add 2 more vertices, then how many different will there be? 8. So if I add 2 more, there will be 16. As you see, for each 2 nodes or vertices we add, number of paths is multiplied by 2. Okay, so here, how many different I have? So up to here, 4 different. So for each 4, either I can choose this one or I can choose this one. So that makes it 8 different solutions. So up to here, if I add 2 more, up to here I have 8 different. So either I can choose the lower way or the upper way, the other one. So it makes 16 different. So I'm just adding 2 but multiplying by 2. So that makes exponential number of paths. If there are exponential number of paths, so finding all the paths, going over all the paths and finding minimum cost of them is really not a good idea. Although it solves the problem, okay, you can solve the problem by finding, of course, all possible paths and then choosing the minimum of them. It solves the problem, but it's not a good idea because there are exponential number of paths. So we should find a better one. Okay, so shortest path from S to V, can it be found without finding shortest path from S to all others? That's my next question. I have shortest path. My question is shortest path from S to V. Can it be found without finding shortest path from S to all others? For example, let me draw it and try to explain it better. So I have S here, and I found a path. Let's say here is an X, here is some Y, here is a Z, not Z, and here is a V. I found a shortest path like this, but maybe there is a T from which I didn't find the shortest path to T. It will be shorter to come from T. So can I find the shortest path from S to V without finding shortest path from S to all others? Are we allowing negative edges? No, we are not allowing negative edges. So let me Can it be found without finding shortest path to from S to all others? So my question is this. Since there might be a shorter path from T to V, then we should be able to find, we should find all shortest paths. If we say this, I think we are making a mistake. So in order to find shortest path from S to V, you have to find shortest path from S to all others. This sentence should be falsified, and let's falsify it. For example, well, sometimes if distance VT, there is no actually edge between VT, there is edge from T to V, okay, is greater than our shortest path so far, we don't have to find distance from S to T. But if it's smaller than, okay, if it's smaller, yes, actually that's a good answer. Let's try to, so what we said here, we found the shortest path from S to V, but maybe there is a shorter path from that comes from T. Okay, so I need to falsify this. You found a shortest path from S to V, okay, but maybe there is a shorter path, there's a vertex T, there's a vertex T, which I didn't have on my path, which you did not find shortest path from S to T. Okay, so from T to V, it will be shorter. How can we falsify this? Doesn't it? So if it depends on graph, then that means you have to find it. If it's depending on the graph, I mean, so in our graph we have specification that our graph doesn't have any negative edges. But in such a case, if you don't allow negative edges and you are asked to find the shortest path from S to V, do you have to find all the shortest paths from S to all other vertices? Do I have to find all shortest paths? So as we describe here, there we found the shortest path S to V, but is there a T maybe that over T it will be shorter? So let's try to see it. Let's start from a smaller one. For example, I have a S and I have, it goes to some vertices. Let's say it comes to this K, it comes to this L, it comes to this M, and this is 35, this is 15, this is 10, and this is 2V. Now, in such a case, do I need to find the shortest path from S to K, L, M in order to find the shortest path from S to V? No, I don't need to. Why? Because if V is already in the min distance, then it's not possible that I can find a lower distance over other vertices. It's not possible that I can find a lower distance coming from K. It's not possible that I can find a lower distance coming from L. Okay, since from the choices, the V is the minimum. What about this one? I have S, it has weight y, which is 3. This is 5 to v, and this is 1. This is 40 to k. Here is, okay. So in such a case, S has weight to v, but do I have to find shortest path from S to v? Before finding S to v, do I have to find S to k, or S to L, or S to M, or S to Y? In order to find S to V, okay, I don't need to find the shortest path from S to K, S to L, or S to M. Why? Because S to K is already bigger than S to V. Okay, S to V is 5, and it's not possible that I will have a shortest path to S to K, and from S to K I will come to S to V with a better solution. So which vertices do I have to find solution? So I have to find the solution. Actually, I will find the shortest path to all vertices that has weight less than shortest path S to V. So this is my conclusion. So before finding shortest path from S to V, I have to find not all the others, but all the vertices that has shortest path lower than V, because these are the possible vertices that may come to V with a lower cost. The vertex that has higher cost, they cannot come to V with lower cost, but the vertices that has a lower cost shortest path, they may have a solution. So before finding shortest path from S to V, we have to find shortest path to all vertices that has weight less than shortest path S to V. So that means if I have a shortest path S to V has cost 10, then before finding this, I should have found all the shortest paths that has cost lower than 10. Before finding this, I should have found all the shortest paths that has cost lower than 10, so that from any other vertices that has higher cost, it's impossible to come here with a lower cost. So this tells me that actually shortest path is another greedy algorithm. You remember the greedy algorithm from last week? What was the definition for greedy algorithm? So perfect. Repeatedly make the locally best solution, locally best decision choice. Decision. That's ignoring the effect on feature. That's the behavior of a greedy man. Okay, so shortest path algorithm, actually we will be doing repeatedly making the locally best choice, so it will keep us optimal thing for that step. Exactly. So this was our greedy algorithm definition. So that's what we will do for shortest path algorithm as well. Before starting to shortest path algorithm, let's work a little bit on negative edges. So negative edge weight. First of all, some short paths may not exist. One of the cases is negative edges. If I have negative edges, in which case I may not have a short path? So let me write my question. When we can't have a short path, when we can't have a short path. Perfect. Negative cycle. If I have a negative cycle, then that means I cannot have a short path, because in such a case, I'll have a vertex so from S to V, and I have a cycle here which has negative weight, 5 minus 7 minus 4, 5. So total of this cycle is minus 1. So from here, instead of going forward to next one, just make one more cycle so that it will decrease the cost by 1. Make one more cycle, it will decrease the cost by 1. So if there is a negative cycle, there exists a negative cycle, makes it shorter by cycling. It makes it shorter by cycling. Not bicycling, bicycling. Cycling. Did I spell it correctly? So in such a case, weight of my short path, what is it? Yeah, it's the negative infinity. Okay. If there is not, let's say, if there is no negative cycle, but there are negative edges, in that case, can I have a short path? Yeah, there exists a short path. There is a solution, but it may be less than 0. Maybe less than 0. Okay. For sure that I will have a short path, but it may be less than 0. Okay. We may work on this. Probably we will work on this next week. So my next question, in which other case I may not have short path? When else short path may not exist? Exactly, when graph is not connected. So I have some vertices, but the graph is not connected. If there is no path from S to V, then there cannot be a short path from S to V. So my if no path from S to V, then weight of the short path is infinite. Okay, it's not connected. So if it's not connected, there's no short path. So in two cases, I don't have short path. The first one is if there's a negative cycle, then cycling will always make it shorter. In that case, short path will be negative infinity. Of course, the extra will not, our algorithm, what we will discuss, will not be working on this. And if there's no path from S to V, if the graph is not connected, in such a case, again, our short path, weight of the short path will be infinity. So we say we don't have a short path. Okay, I want to discuss one more property. That's subpath of a short path. Can I be sure that it's also a shortest path. Let's say is a shortest path. Is it? So Kaushik says it's always a shortest path because you can prove by contradiction. Okay, let's try to visualize it. Let's say I want to have from S to V contains K. Okay? Not for original two vertices. What you mean exactly, Ben? Not for original two vertices. Shortest path. I found a shortest path from S to V which has K in the middle. So it comes like this, somewhere at K, and it comes like this to V. Okay? So we assume that from S to V, this is the shortest path. So are we sure that S to K, this is the shortest path? S to K, is this the shortest path from S to K? Also, is this the shortest path from K to V? Subpaths, are they also shortest path? Yeah, it's for sure, as Kaushik says. Why? Because you can have proof by contradiction. If, let's assume that this is not the shortest path from S to K, there is another path which is shorter than this. In such a case, then this full path cannot be the shortest path from S to V. In such a case, this path, the alternative path from S to K, K to V would be the shortest path. Okay, so if there is a shorter path from S to K, then that must be in the shortest path from S to V. Okay, then I wouldn't have chosen the upper one, then I would have chosen the shortest path from S to K. So any subpath in shortest path is also a shortest path.